Sí, bueno, tampoco mucho, pero fui a cenar y sentando por el paseo, que es increíble. Sí, no, es increíble este verano. Es curioso porque había venido aquí a competir en atletismo. Sí, pero nunca había... Cuando veníamos íbamos solo al estadio, pero no. Entonces sí había estado con los padres cuando era pequeño. Y sí, luego compitiendo en atletismo, pero claro, cuando venía a competir, sí, íbamos en bus y nos traían al hotel y del hotel a la pista y se todo como unos 15 días. Bueno, hice un poco de todo, pero sobre todo he hecho atletismo siempre. Ahora no estoy tan informado. Sí, intento ir una vez por semana, pero no sé. Responded to that to 1 you cover the two or from 0 to 1 0 to number. La distancia que llegamos puede ser es un medio punto. Sí, exacto. Empiezas sprint y llega un punto que no puedes y dices, sí. Esto es lo que me decía mi hermano. Tú, cuando tu cabeza sería más en el 400. Eso sí que es también sí que empiezas muy rápido y sí, cuando mi entrenador me decía, no pienses tú. No te da mucho tiempo. Sí, creo que el récord del mundo está en 1:40. Son menos de 2 minutos. Very easy to do the SSH between this and el tiempo no lo conté muy bien, pero bueno, es cuando hay algún no, pero sí que es aviso. Sí, avisan de cuánto quieren 10 minutos. No, o sea, no todos los 10 minutos, pero más 40, me avisas. Sí, que es más 40 minutos, ¿sabes? Razonable, eso suele ser una conexión mucho más baja. No hay muchos si son muy largos o gente que va muy bien. Por eso somos utilizados muy flexibles. Sí, creo que es la primera vez que voy a echar de información. Siempre digo 30 o 10, muchas funciones. Sí, tengo años pensando tengo una historia que sí.
Okay, good morning. So welcome everyone. So it's a pleasure for me to introduce Pau Farrera. So Pau, he's a researcher in Munich, at the Max Planck Institute of Quantum Optics in Munich. So Pau, he made his PhD in ICFO, the first in the group of Hugh the Rydberg, correct the pronunciation?
Rydberg.
Sorry for that. And he spent a few years in ICFO up to 2018, if I don't remember. 2018
or 19.
Okay. Then he moved to Munich, to the group of Rempe, Professor Rempe in Munich in the MPQ. And then he comes here to San Sebastian to explain to us his research during his scientific career. So thank you very much for coming, Pau. Yeah, we are very glad to have you here. And
thank you. Okay, yeah, so thank you everyone for being here. It has been great yesterday and today to be hosted here at the International Physics Center, and we talked to some of the researchers here. So yeah, today I will be talking about my path into studying quantum information, quantum optics experiments with laser-cooled atoms and optical cavities. And this is some work that I've been doing at IPFO in Barcelona and at the Max Planck Institute of Quantum Optics. And the experiments that I've worked with during this time, you can see some pictures here. So here there is one cloud of atoms which are pulled by lasers here at the center of this picture. And here, okay, you see this setup at the Max Planck Institute of Quantum Optics, where we have a single atom coupled to two optical cavities. But okay, I will talk about this more in the next slides. So first, just to start on a personal side. So of course, like, yeah, you have super beautiful city here in Donosti. And I have been here a few times, once with my parents, last summer on my own. But I have to say for me that the nicest memories were in a kind of hidden place here in the city, which is here in the Antonio Elorza Velodrome, where I was competing in athletics some years ago, 2000, sorry, when I was 16 to 18, and I came here a few times. So yeah, today I will be talking basically about individual particles. So these could be individual atoms or individual photons. And I just wanted to start with this quote, just to say that the experiments that I've been doing deal with these individual particles, so individual particles of light, individual atoms. And then we study some surprising effect when these different objects interact. And then we try to look for applications based on these effects. And this is something which is not new. So this has been done by many scientists before me. And here one example is this experiment, the so-called single atom laser, which was developed in Munich, where there is an atom oven which releases atoms. Then these atoms go through a velocity selector. Then they cross a microwave cavity, and then they interact with intracavity microwave photons. And then they are detected by image Hamilton. So this this experiment, which was developed in Munich and in Paris, was one of the first experiments which deal with these individual particles, and was provided one of the first evidences for the quantization of the electromagnetic field. So nowadays, the experiments that are done in this direction are a bit different. And okay, Professor Gerhard Rempe is one of the pioneers in these experiments. So they, in this case, now we have individual atoms which are coupled to optical cavities, or not microwave cavities in this case, and they interact with flying single photons. And so what allows us to have the atom in this position of maximal coupling to the cavity and keeping it there for 30 seconds in our experiment is actually a few things. So on one side is laser cooling, and here, it's explained in very simple terms. Laser cooling involves the Doppler effect that atoms experience when they interact with light in such a way that in the atom there is a velocity-dependent force which kind of removes kinetic energy of these atoms. So that's how we cool the atom. We shine counter-propagating laser beams to the atom, and we cool it with this effect. Another important effect to keep the atom at the position is then to trap it. And for this, the technique that we use, it's called optical dipole trapping, which is based on the AC Stark shift induced by light field on an atom, which then brings the atom at the position of maximal intensity of the laser. Okay, so at the moment there are like many different platforms that one can use in order to study the interaction between quantum light and matter. And okay, here you can see many platforms based on trapped atoms, vapors, solid systems like superconducting circuits, optomechanical systems, then diamond decay centers. So there are really many possibilities. And during my PhD and postdoc, I've been working with laser-cooled atomic clouds, or cloud of atoms, and another system with a single atom coupled to so exactly, I've been performing experiments in both the group of Hugh de Riermaten and the group of Professor Gerhard Rempe on these two systems. And indeed, what we do is we study the interaction of these atoms, atom cloud at ICFO and single atom at MPQ, with photons which can either interact or be emitted by this atom. And then we encode quantum states on these individual particles in the atom and the photon. And then we study effects such as entanglement, for instance, different quantum physics, and which can then be used for quantum information science and applications. So, quantum information deals with what happens when you encode information in these individual particles. Okay, so what applications can one do with encoding information with these particles? One possibility, for instance, is to perform quantum cryptography. So this is cryptography, so send secret messages where the security of the protocol is not based on computational power, but is actually based on laws of quantum physics. So it's based on the Heisenberg uncertainty principle and the non-cloning theorem. Another possibility is to perform quantum algorithms with this information of encoded in quantum particles. And here the interesting point is that in quantum physics, you have the quantum superposition effect. So you can be in superposition between two different states. And then you using this information, so this exactly this information which is encoded in the atom, then you can build in principle. There are some theories who propose this. You can build then some algorithms which in principle can be more powerful than supercomputers. Okay, and when you kind of the advantage in this context of using interfaces which deal with the interaction between photons and atoms is that in atoms these are good to store and process and synchronize the information, because you can really keep the information there in the atom, while individual photons, they travel over long distances easily, like through optical fibers or through free space. So then when you want to communicate information over long distances, then it's good to use these individual photons. And okay, there are some scientists like Jeff Kimball and many others who have this, this vision to at some point have atoms distributed over several locations, and then that they exchange quantum states over some long distances, which could be then used to test like fundamental quantum physics experiments by distributing these quantum states over different matter systems, or to build quantum communication repeaters to extend the quantum communication distance, or to perform distributed quantum computing. So if you have different quantum computers, you could also connect it through this, or the Bayes-independent quantum key distribution or distributed quantum systems. So there are some applications that some people propose and that researchers are exploring. Okay, so my journey started at the Institute of Photonic Science in the group of Professor Hugh de Riermaten. And as I said before, here we had this atomic, so this cloud of different atoms, which was cooled with lasers. Exactly. And the advantages of such a cloud is that first, because the atoms don't interact much with each other, then you can preserve so quantum states, because quantum states are very fragile, so they can kind of be modified with interactions. So if you encode the quantum state in this cloud, you can keep it for long time. The second advantage is that, because you have many atoms, there is a strong interaction with the light compared to a single atom. And you can also encode, because you have many atoms, you can encode different states of information. So you can do some and moreover, you can excite these atoms to highly excited Rydberg state, so-called. So where there you can have strong dipole-dipole interactions between the atoms, and this can potentially be used to process this information. Okay, so that's a picture of the experiment that I worked with during my PhD. So we had this cloud of around 10 to the 8 atoms that we cooled to a temperature of around 40 microdegrees above the absolute zero. Okay, we use 87 rubidium atoms. And indeed, we study correlations between excitations, so one atom changing spin, changing state in the cloud, and then being correlated or entangled with and the scheme that we implemented is the so-called one-looking Sirac solar scheme, and here which was developed in Innsbruck, and here the idea is that in these atoms you have two ground states, so two different states with very low energy, and then one excited state with higher energy. And then what we do is you send a laser pulse to this cloud of atoms, and through a process called probabilistic Raman scattering, then there is a photon which is then emitted into a particular spatial mode, which can be correlated with an excitation in the cloud, or would also be then we wait for some time, so we keep this excitation in the cloud, and then we would send like a pulse, a second pulse. We call it a read pulse. But what it does is then maps this excitation, which was in the cloud, into a second photon, into a second photon. And the point of this kind of experiment is that we don't only have one excitation in the cloud, but we have a collective excitation. So this is like a single excitation, which is delocalized over several atoms in the cloud. And because we have this like superposition of different atoms being excited, then there is a phase matching condition, which means that then in the end we then emit this photon into a very well spatial mode, very efficient. So in the end, we have these two photons propagating in opposite directions, which they can be correlated or they can be entangled. So the first experiment or one of the first experiments I did in the PhD, or one of the first goals, was then to transfer these photons emitted by the cloud of atoms into a crystal. And the idea here is first that in order to do this, you need to change the spectral properties of these photons. And here the point is that if the photons are if the photons are Fourier limited, then the spectral properties of these photons they depend on the duration of the pulse. So that's what we did. We tuned the duration of the excitation pulse and of the which then changed the duration of the photon. We saw in the experiment that this we can do it over 2 orders of magnitude, from around few nanoseconds, few microseconds to a few tens of microseconds. And we saw that this limit of few tens of microseconds is actually given by this coherence of the spin excitation, like encoded in the cloud, as we observe when performing a theoretical collaboration with Professor Nicolas. The second thing that you need if you want to transfer this photon from the cloud to a crystal is to change the frequency, so change the color. And this we do it via quantum frequency conversion, and in particular difference frequency generation. So here the idea is that you mix these individual photons with a strong laser beam at 1569 nanometers, which then by a process in which the frequencies are kind of subtracted, then this generates a photon at 1552 nanometers. And then this photon, we send it to a different lab. We mix it with a pump at 994 nanometers, and then through some frequency generation, then we get a photon at 606 nanometers. I forgot to say that we actually, so this is not only a photon, but it's a time-being qubit. So this is a photon delocalized over two different like temporal or spatial windows, and then this time-being qubit, we map it into a crystal, and then we retrieve it. And this we do it with a fidelity, which tells you how good is how similar is the state of this qubit with respect to the input qubit of 85%. And exactly. So this was the first time where quantum states were transferred photonically from two different systems with different atoms and different phases of matter. Then the second, or another goal of my PhD was then to generate entanglement between this excitation in the cloud and photons which are emitted in this time-being qubits, photon delocalized over two groups. And so generating a time-being qubit, that's kind of easy. It's not a problem. However, what is more difficult is to have an excitation in the cloud, which is delocalized in time, kind of. So that can be retrieved in multiple times. So in other words, you need a kind of qubit basis for your excitation, so an orthogonal qubit basis. And the way we achieve this is actually with a magnetic field. And here the idea is that if there is no magnetic field, then you keep the coherence of the excitation in the cloud, then you can have a high efficiency in the photon readout, which is constant over time. However, if you then have a magnetic field which is not zero, then because you have superposition of different energies in the phase evolution of this collective spin excitation, this kind of phase, this kind of energy makes this collective excitation kind of beat, kind of, and then you see this beating in the efficiency of this excitation into transfer it into a photon. So the trick that we did in the experiment is to then have two excitations delocalized in time. One with half this rephasing period. And if you do this, then what you can do is to kind of send two excitation pulses which generate this time-beam qubits, or superposition between two photons into two time beams. And then this excitation in the cloud can be entangled with this photonic time-beam qubit. And then you can later map out, with an intrinsic efficiency limitation of 50%, you can then map out the excitation into a photonic time-beam qubit. Okay, and then these two photons, these two photonic time-being qubits can be entangled, so can be in this state. Okay, and then this provides so okay, the way we verify that our photons are in this entangled state is by violating the Bell inequality, which okay, in the end it's an inequality which tells you if so in the end it's based on four correlators for the two qubits, and then if the sum of these correlators is higher than 2, then this tells you that you have this entanglement, so this correlation which is stronger than local realism. However, if this value is lower than 2, then okay, this would tell you that okay, it could be described by a theory which which fulfills both locality and realism. Okay, and then this project evolved had different aspects of it, and we extended it later in having this excitation delocalized over this figure 6, but okay, maybe it was I think we went up to 10 temporal modes using then magnetic field gradient. Okay, and this project also then actually went a bit further in another direction, which I found it kind of nice. So this was called the so-called big Bell test. So this was kind of this Bell test I just very briefly explained, which was performed in different laboratories in the world. And this Bell test actually backs forth to the so-called Einstein-Bohr debate. So in this debate, the debate was kind of on the interpretation of quantum physics, and Einstein had a view of that nature should be local. So whatever happens at one place only depends on things that happen at this place and realism. So this means that the properties of objects and everything are well defined. However, Bohr had a different opinion. So he thought that in quantum physics there is this superposition, right? So he thought that nature is in this superposition until we observe it, and then then the state collapses exactly. So actually, this was a debate for many years, and I guess they had. I was not there, but I guess they had many nice discussions. I would actually like to listen to them. Not possible anymore. However, John Bell then came with a solution. So he said, okay, for these entangled states, which are these kind of highly correlated states of two photons or two atoms or two electrons, so two different quantum systems. One can perform a test, and this is called Bell test in honor of him, where the idea is that these two particles or two entangled particles, they go through two measurement devices, exactly. And then in these measurement devices, they perform two different. They can perform measurements in two different bases, and they can also get two different results because they use qubits. So qubit can be only in two different states. And as I said before, so there is this Bell inequality. So this is based on these four correlators. So these correlators are just the product of this result times this result. So these correlators can average from -1 to +1 because you always average over different events in the experiment. And what John Bell said, I think his inequality was a bit different, but then also Clauser, Horn, Shimony, Hall, they modified it a bit, and then they said that if you add up these three correlators and this and you subtract the fourth one, then the result that you should get with local realistic theories would be that you have some of these four correlators are lower than 2. This yeah, these experiments have been performed since many years by many different like scientists all over the world. So by Alain Aspect, John Clauser, Anton Zeilinger, they have performed many experiments, and they received the Nobel Prize actually quite recently. And they received it because they observed in their experiments that the result they obtained is 2 times square root of 2, which is in contradiction with this Bell inequality. So yeah, it seemed according to this to these experiments, one would say that maybe Niels Bohr was correct about this. However, there is this is not the end of the story, because there can be loopholes. And loopholes are kind of like imperfections on your experimental implementation, which don't fully match with the theory. So of course the theory is mathematics, right? So it's it lies in mathematics, it's mathematically correct. But then when you do the experiment and try to mimic these mathematics, then there can be always mismatches. So that's, and then the argument was then maybe nature can somehow explore these loopholes to kind of trick us into thinking that there are these correlations, but apparently they are not. And yeah, one of the loopholes there are different ones. There is the detection loophole that had been closed, the locality loophole. If you, for this, you need to move the entangled states very far away. And another loophole is the freedom of choice. And the freedom of choice loophole means that the person who however these bases are set, this has to be independent both in the 2 experiments, but also independent from the source. So this selection of bases have to be fully independent from the source and from the two measurement selection bases. And in previous experiments, this had been done using quantum random numbers. And for quantum random numbers, what you do is you say if quantum mechanics is in a superposition, then once I measure, I will get one of the states, and this will be random, and this will be random given by nature. So it's like true randomness. So this was the assumption which was done in these experiments. However, there is one question. Yes. Sorry. I forgot. So the solution was to use quantum random numbers, exactly. So to use this quantum random numbers, and however the criticism was that maybe you are using in your assumption what you are trying to prove, exactly, because we want to try, so we want to prove that this quantum superposition exists, but however we are using it to assume it. So there was there is an alternative solution if you want your 2 different measurement bases to be independent, which is to use human free will. Because if we agree that as humans we have free will and we can do whatever we want, then we can select the bases, and then the two basis selections are fully independent. So this is what it was done. So in different experiments in the world, and here you can see some numbers of the experiments that were performed. On the 30th of November of 2016, 100,000 participants. They selected 10 million binary choices, which were then distributed over 13 different experiments in different points of the Earth. Different experiments got different results. In yeah, in the day of the experiment, I have to say we didn't violate inequality in my experiment because we had started very, yeah, our experiment was not ready, the experiment. However, yeah, after some time, we violated Bell inequality with 2 times 2.29 plus minus 0.10. Yeah, by using this stored human random set. Yeah, however, in the day of the experiment, we could still see high correlations in the 2 photons. And okay, here I just have a nice video which I copied, which I had stored in my home phone. So this is just yeah. So here you can see kind of the different basis settings. So like the vertical line represents like the basis setting, and as you can see, they are changing, and they were changing from human random numbers that were collected by all the participants and coming into into this PC that you are here and going into the different devices in our laboratory. So yeah, this was yeah, it was a nice project to see like so many people like contributing to to kind of yeah, adjusting the measurement basis in my laboratory. So of course it was like, yeah, it was a kind of tiring project because yeah, we needed to have the experiment ready by a given date. So usually when you do experiments, you don't care which day it works. You just wait that it works. But that day it was okay. This day we need to have the experiment ready. So okay, we spent several weekends working and some short nights. But okay, in the end we were very happy that it worked. And as you can see, the evening of the Big Bell test, we celebrated with some chocolate and so on. Okay, however, yeah, recently I was thinking, so, for this Big Bell test, we were using the participants had to use a video game to type the random numbers, so they could do it in their phone. Okay, well, there was kind of an oracle which was trying to predict your random numbers. And okay, recently I thought that maybe this is not the best idea to generate human random numbers, but okay, that's how it was done. Anyway, so yeah, yeah, during my PhD, I also worked on different experiments. So what we were doing is exciting atoms into high exciting Rydberg states, and then we were studying the interaction, the dipole-dipole interaction between yeah, exactly, 2 different atoms excited in these high Rydberg states. And okay, we did some experiments, some related to storing single photons in these highly excited Rydberg excitations, okay, using electromagnetic induced transparency, or then to generate single photons, so the single particles of light, by using this cloud of atoms, which is then excited to this Rydberg. Okay, so yeah, my next move was to go to the Max Planck Institute of Quantum Optics in the division of Professor Gerhard Rempe. So the experiments that he has, they deal with a single atom coupled to a high finesse optical cavity. And here the idea is that individual photons interact with this atom called via these cavities. So this cavity is based on 2 mirrors with high reflectivity, and then the photon can bounce back and forth within the cavity and experience a strong interaction with the and what I was really excited about this project is that this so a single atom in a given state can introduce a pi phase shift on the state of the photon. So this means that the photon kind of shifts in time by half oscillation period. And this can be done by only a single atom in a given state. And okay, this had been used in the group. Okay, Stefan Rydberg was one of the main, also a leader in these projects, where they had been implementing these experiments and implementing qubit gates between the atom and the photon, or qubit gates between two different photons mediated by the atom, or qubit gates between two different atoms but mediated by the photon. And also, another project which I really like is that they also detected a single photon without destroying the photon. Okay, so the experiment that I showed, you can see it here in this picture. So this was based in a new generation of optical cavities, and this is kind of based on fibers. So these are kind of fibers which have been cleaved and where CO2 laser removes some part of the tip of the fiber, and it gives it a high quality spherical surface. So in our experiment, okay, we call it the cavity X experiment because these are two crossed fiber cavities, and sorry. Okay, and what you can see here in this picture is that we have mirrors to then send light to the atoms. Then we have here different fibers which then are brought to the center. We have a stick slip piezo actuator which allows to bring the fibers to a given point in the exactly at the proper position, and then we have piezos that we can use to kind of shift these fibers and such that the cavity has the appropriate length. And if we zoom at the center, then we can see these crossed cavities. These four fibers coming together, and we have kind of a single atom trapped at the center. And okay, the idea is that because these cavities have a very small mode volume, so this means that the two fibers are very close together, and the mode waste is very, very small. Sorry. Okay, there is a strong coupling between the atom and the photon. And then this leads to high cooperativity, which is a ratio between the coupling and the decay loss in the cavities of around 10. Okay. And our idea was then to study different schemes in which two different transitions are then coupled to the atom in a different configuration. Okay, so the first experiment that I was involved in was to non-destructively detect a photonic qubit. So here the idea was to reflect photonic qubits from one of the atom cavity systems, and then the point is that this interaction would kind of induce a phase flip in the atomic state, which then could be read out via the second cavity. So yeah, exactly. So in few words, the way this works is that you have two atoms, one atom in which has, three levels are used, in which if you have the atom in one state which is not coupled to the cavity, then if a photon enters the cavity, it can bounce back and forth, and then it can exit the cavity via the same mirror with a pi phase shift. However, if the cavity, and this is because the cavity is single-sided, so this means that the transmission of this mirror is much higher than the transmission of the other. Okay, so in this case, there would be a pi phase shift on the atom photon state. However, if you have the atom in this state, which is then coupled to the cavity, then there is a normal mode splitting of the atom photon energies in such a way that the photon has no way to enter the cavity. Then in this situation, the photon is reflected by the first mirror, but then it doesn't acquire pi phase. So the idea then is to have kind of a photonic qubit, which is reflected by the first cavity, and then you can see when through this interaction, then the component with the atom in state one acquires a pi phase shift, and then the point is that if the state of the photon and the state of the atom remain separable after this interaction, then this pi phase shift happens in the state of okay, so that's what we did. We put the atom initially in a superposition by using microwave radiation. We then rotate the state of the atom from state zero from one superposition. Initially we rotated with microwave into a superposition state between 0 and 1. Then we reflect the photon, and then we when the photonic qubit is reflected, then there is a pi phase shift happening on the state of the atom. Then we apply a second microwave rotation in such a way that if the photon rotated into state 0 minus 1, then it rotates into state 0, and if it rotated in state 0 plus 1, then it rotates into state 1. And then finally, we measure if the atom is in state 0 or in state 1, and this tells us if the photonic qubit was reflected or not from the cavity. Exactly. For us, the advantage of using two cavities is actually that we can have one cavity in a transition which is suitable for the interaction between atomic and photonic qubits, exactly. And then we have the second cavity in a transition which is then suitable for this last fluorescent state readout. So this is a cycling transition. So it's a transition in which the atom can get excited and de-excited multiple times, and then emits many photons into the cavity, and these photons can be detected and tell us in which state is the atom, and therefore whether this photonic qubit was reflected or not from the cavity. Okay. So that's what we did in the experiment. So this here you can see the kind of histogram of events. What you can see here is that we have the first microwave pulse. Then we reflect the photonic polarization qubits from cavity. Then we have the second microwave pi over 2 pulse, which kind of rotates again the state of the atom. And then we detect whether the atom is in one state or the other. And that's what we see here in the end. So if photonic qubits, if no input photonic qubits are reflected, then the atom is in one state, while if input photonic qubits are reflected, then we see a low level of fluorescence counts, which tells us that the atom is in the other state. So in the end, by this kind of level of fluorescence counts, then we can say whether the atom is in one state or the other, and therefore whether the photonic qubit was reflected by the system or not. And okay, here are some numbers of this detector. So once the photonic qubit was reflected, then we can kind of detect it by measuring the state of the atom with an efficiency of 80%. The loss of the photonic qubit in the interaction with the atom was around 30%, if I remember correctly. But once it's reflected, we can detect it with 80% probability. The dark counts of this detector are 3%. So kind of in 3% of the times that we kind of try to measure this photonic qubit, then the atom tells us that there is a photonic qubit, but there is no photonic qubit. What else? Sorry. Exactly. And the qubit fidelity, which tells you how similar is the qubit which is reflected from the qubit which went in. This is 96%. Okay. After the work we then 5 minutes. Okay. Then I should maybe speed up a bit. So after the work, then we proposed some applications. So we thought that this detector could kind of be used to kind of detect photons which are propagating in kind of a quantum communication link. Okay, it could do so by telling the emitter and the receiver whether this photonic qubit was lost in the wave. So kind of this detector could tell if this photonic qubit is propagating or not. Exactly. And this has been predicted in different papers. Then they said that this then can be used to kind of save time and expensive resources. For instance, like if you have entanglement over long distance, I mean, this is very hard to produce if you have entanglement between two very different labs. This is very difficult to do. And therefore, if you want to kind of use this entanglement to teleport a single photon, you want to do only this if your photon is there. And therefore, with such non-destructive detector, you could do that. Then you can also perform loss sensitive qubit measurements. So you can, before measuring your qubit, you can use this non-destructive detector to be sure that the photon is before the detector. And then this has some applications in quantum cryptography. Okay. Yep. And finally, this detector can be used to kind of enhance quantum communication, but it can be also used to attack it. And for instance, there is one attack in quantum cryptography. So this cryptography I mentioned before that uses quantum states of light. One of these attacks is called the photon number splitting attack. So in this attack, what you do is you kind of, this happens when you are not using single photons. So this happens if you are using like sources which may have 1, 2, or 3 photons. So then what you could do is kind of split these photons and then measure the information in one of them and then propagate the other one. So then you could kind of leak information from the measurement link. And to perform this attack, you need this this non-destructive photonic qubit detector. yeah, after this project, what we did is to then. Sorry, you should tell me when I should finish. Yeah.
Okay, go ahead.
Okay. Yeah, because I don't track time. Okay. Yeah. Sorry. The next project we did is to kind of study the situation in which two different transitions are coupled to the cavity in such a scheme. So where one state is coupled to an upper state with the herald with this with one cavity, and then this state is coupled with a higher state with another cavity. And the two photons then emit. The atom emits then two photons in the two cavities. And of course, photon pair sources are not new, so they have been developed in many different experiments, and for instance, with atomic ensembles or with spontaneous parametric down conversion. However, with these platforms, there is always a trade-off between the efficiency to generate the photons and the multi-photon component generation. If you want to make it more efficient, then it may happen that you have two pairs instead of one, which then would kind of degrade your entanglement. This can be solved in quantum dots embedded in a cavity. So here the idea is that there is a kind of bi-exciton-exciton decay in quantum dots, which can then produce also two photons. However, when you do this when you do this with a single cavity, then it may be difficult to then couple these photons into a single mode fiber because, in current experiments, it was mostly done with different, slightly different modes. While if you do this with low photon, and moreover, this poses also some limitations in the photon indistinguishability of photons from independent sources. Another advantage when you for using this scheme is that in rubidium there is a telecom transition. So there is a transition with telecommunication frequency, which is similar to the one used in telecommunication, in quantum, in communication in general. So at 1529 nanometer. And the idea is that we have a proposal in which single photon could be generated in this upper transition, this telecom frequency, and entangle with the and in the group there is a proposal on how to then use this to build a quantum. So that's what we did. We excite the atom to this excited state, then we let it decay. It emits two photons in the two, so one in each cavity. The efficiency with which we have two photons, one in each cavity, is 22%. And the here you can see the histogram of events, and and this if we compare this decay to the lifetime of the entangled state, then this gets a cooperativity of 1.2. So when we measure the single photon statistics of this light, so this can be measured by the autocorrelation function, so-called or Glauber autocorrelation function. Then we measure actually very low values, and these are distinct for individual. And if we compare then these photon statistics and and we consider the low photon statistics and the photon pair in fiber efficiency, then we get our results are significantly better with what is achieved with sources of SPVC using two-mode squeeze. However, one drawback is that the two photons are temporally correlated. So you can see this here. There is a temporal correlation of 10 nanoseconds compared to the duration of the full duration of the photons of 100 nanoseconds. And this poses limitations when you want to kind of interfere photons emitted by independent sources, because for them to interfere, they have to be indistinguishable. However, the advantage of using two cavities is that then you can have one cavity in exactly. You can tune the parameters of one cavity with respect to the other cavity, and then by doing that, you can in principle increase this interference visibility to 96%. In principle, okay, the theory tells that this is possible. Should I finish? Or?
Yeah, roughly, you may have your conclusions.
Okay, so there you go. Okay, sorry, I took a bit more time than I was expected, so I will be very fast on. Okay, this was just a theory project to kind of explore the strong coupling regime. So okay, some simulations maybe for the future. This is like an extension of the scheme in which we then use the source to kind of generate entanglement between light and the atom in a heralded way. So okay, when there is a herald, when there is one photon in one cavity, this tells us that there was entanglement between the photon in the other cavity and the atom. Okay, we measure these states with like wave plates and PVS and detectors for the photon, and microwave and cavity and photon generation for the atom. Okay, we then reconstruct the atom photon density matrix, and we get fidelities of 87% once a photon heralds the entanglement, and an efficiency of 68, which is better to the case in which we don't use the entanglement. So yeah, just as an outlook, so okay, we can maybe envision sometime in the future where there are these, I don't know, quantum communication links between atoms, which kind of exchange individual quantum states of light, and then these kind of nodes can kind of detect them, so we can know when these photons are emitted, when these photons propagate, and when these photons are received, so we can fully track the distribution of photons. And okay, if we want to build this, we want to go to long distances, and now in Munich we have this long link between Munich and Garching, where we are currently exchanging these quantum states and distributing entanglement. For this, again, we need to change the color from 780 to 13 nanometers to go to long distances. And we have some preliminary results which kind of show the entanglement between an atom in Munich and an atom in photon, and a photon in Munich. An atom in Munich and a photon in Garching. And okay, in the future, we may want to then entangle two atoms, one in Garching and one in Munich. Okay, that's for the future. And okay, I would just like to thank like all the people with whom I worked during my PhD and my postdoc. I was really fortunate to work with really outstanding scientists and outstanding people in both places, in ICFO and MPQ. And we also had like a lot of support from, of course, like funding from many different institutions. Support from mechanical workshop and from administrative and institute staff. So that was really great. I wanted to talk a bit about the project that Francesca was proposing for here, but since I'm out of time, I just skip this part and just go to the conclusion. Okay. Oh, yeah, exactly. So, okay, yeah. Sorry, sorry for the extra time, but okay, I just conclude. Yeah, very briefly. So as I said, okay, I'm now, yeah, I'm here to have to apply for this position here at this center. So okay, I'm interested in working, of course, in this quantum light matter interfaces where there are these different. The idea is to have these different nodes distributed over different places, exchanging quantum states. So yeah, who knows? Maybe in the future there is one of these nodes here in Donosti. Who knows? And yeah, you know. So okay, I like traveling, and I like traveling by train actually to different places. And recently I did a very nice trip when I went from Munich to then Florence, Firenze, then Barcelona, and then Madrid. And I visited in these different labs, different groups in which where they work with these different quantum light matter interfaces. So this was kind of an interrail tour, or maybe a quantum node interrail, because I was visiting different labs. But yeah, what was actually, you know, with this trip, sometimes you find nodes in places where you don't expect. And I was actually spending one night in Avignon. I visited the Palais des Papes, I think it's pronounced in French. Yeah, you know, I was actually happy to see that apparently in holy places, they also like atoms, and in this case, coupled to acoustic cavities. You know, there are these acoustic resonance effects in these walls. Yeah, at the beginning I was wondering like what could be this like a big bar here at the center. But then I thought, okay, maybe if this is the magnetic moment, maybe this is this dysprosium atom, which is one of the atoms for which Francesca Ferlaino is very very well known and has done many interesting work. So yeah, sorry for being late with the time. Sorry, and with this I thank you for your attention.
So thank you very much, Paul, for this very nice talk full of interesting results. So for those of you who don't know, perhaps I should have provided the context at the beginning of the talk. So sorry about that, Paul, because you might know that. So we have the plan of opening a new laboratory on quantum technologies that will be led by Francesca Ferlaino. Francesca is a researcher at the University of Innsbruck that is already affiliated to the IPC, also part-time affiliated, and the idea is to have a lab here in which there would be also another researcher, a young researcher that could be every day at the lab working with Francesca. So we opened an ICROBAS fellowship ad hoc position a couple of months ago, and so there was, let's say, several applications, and there were at least two of them that were very good. One of them is the one of Paul, that he was presenting today his work, and that he would be, in principle, interested in occupying this position. So sorry for not having provided the context first for those of you who didn't know about that, but now you know, and now you can also ask some questions to Paul about his talk, if possible. If there's anyone interested online, please send the questions also to the chat, that I will be taking care of reading them. So any questions, comments? Yes, sir?
One general question I have, thank you for the question I have is about the fidelities that you showed, and how would you go about pushing them towards one? The measurements or the entanglement. Or maybe I should first ask, what is it that keeps them away from one, and is this something that you can access and improve on?
Yeah, it really depends on the experiment, actually. So, for instance,
let's talk about the non-destructive measurement.
In the non-destructive measurement, if I remember correctly, there was a kind of, as I said, you know, for this detector to work, the polarization state of the qubit has to be separable to the spin state of the atom. However, we had a small entanglement between the atom and the photon, and this was one. I remember this. We did some calculations, and we found that there is this small entanglement because of imperfections in the scheme, in birefringence in the cavity, and I think also because the cavities are not perfect, they have losses. So, I had one slide with imperfections of the detector, but I'm not sure if I have it here. If you want, I can try to find it. Or maybe okay, later if we can talk about this. But yeah, I have one slide that I didn't have time to put this, where I kind of discuss the different limitations of this detector.
If I believe in the classical world, I would maybe say that nothing is random at all, and then how would this loophole in the Bell test be closed by asking 100,000 or I don't know how many people, or making them do the choice? I mean, this is also not a random choice, then, right?
Yeah, sure. Yeah, that's a loophole which cannot be closed.
No loophole is closed.
So if everything is determined, then sure, yeah, there is this we will never find out. Yeah, there is no way of finding out if everything is fully determined. Exactly. So the question is whether we believe that there are random events, and also whether we believe that we have free will, right? That's okay. That's a question. Like, of course, okay, that's more a philosophical point of view, right? Whether we have free will, whether animals have free will, whether I mean that's philosophical question. Yeah, exactly. Yeah. But this, I mean, that's the point. This is an assumption, so it's not. We are not telling, okay, humans have free will or not. This is just an assumption we made for the experiment. This was a new assumption because the previous assumption in previous experiments was that, okay, that quantum random numbers are fully unpredictable. That was the previous assumption. Now, in this experiment, there was the assumption that, okay, that humans have free will. Yeah.
Yes, sir.
Basically, if you can, so it was a pity that you didn't talk about what you plan to do here. So maybe if you can just say, is this about also quantum communication, or is it about atom-atom interaction? So what is kind of what was the main direction of the research?
Yeah, sorry, I didn't have time to go through this. I have some slides prepared for the project. Yeah, exactly. So you probably know better than me, but the call is open for quantum computation and information with a programmable neutral atom arrays. So these are atoms in arrays, and of course, I mean, these neutral atoms in arrays now are very popular in different places in the world. They are using them to build quantum computers. Okay, this is the very famously the work of Mikhail Lukin in Harvard, where he has these atom arrays, performs gates between the atoms, and it's going in the direction of quantum computing. In Munich, that's a quantum simulation lab, but then within Immanuel Bloch division, there was quantum computing startup which started up, so Planck QC. So really this technology of atom arrays, to me, when I started the PhD, it was one of the kind of least promising ones among all of us, among all the others. But now it seems to be a quite promising one. Yeah, exactly. But I have to say I'm not very expert in quantum computation, so this is maybe something I could explore here. But of course, what I'm more expert and that I could continue exploring here is then quantum light matter interfaces. So maybe this you can also do it with this type of atoms if you let them interact with a cavity. But this is something I've been starting to think a bit, but I need to think a bit more about it. Yeah.
Yeah, I think, I mean, the general idea, just let's say complementing this is, let's say, the work of Francesca has been based on these kind of systems, and then she would like also to move to try to study which are these possible applications in terms of computing, let's say, from a very basic perspective, and then so this vision of, let's say, the interaction with cavities, for instance, that would be something like, in addition to that, taking advantage of the expertise of Pau. But the original plan was rather, it can be summarized in this title, you know, this quantum computation and information read.
Yeah, exactly. So these prosium atoms, okay, sorry, I didn't. So yeah, you know, this is the periodic table, right? So yeah, like people try to, like the atoms which are mostly laser cooled in most of the labs would be like alkali atoms, so atoms with one electron. But yeah, Professor Ferlaino is really expert in then cooling like atoms with multiple electrons in the valence band. So yeah, especially she's really expert with erbium and dysprosium, and I think now she's starting with erbium experiment as well. Okay, yeah, so she's really expert on this. And these atoms have some nice properties that the alkali atoms don't have, and then the idea would be to kind of see whether these properties they bring some advantage with quantum information. So yeah, you know, like Francesca is really expert in quantum simulation. So she has developed this kind of super solid phases that she then relates to neutron stars. Okay, well, I have to say I don't fully yet understand it, but it sounds really fascinating. And I think now she also wants to explore a bit like more the quantum information perspective and see whether these atoms that she knows how to use for quantum simulation, whether they can also be useful for quantum information. Yeah, that would be the idea. Yeah.
Okay. Any other comment, question? So if not, we thank you again very much, Pau, for your visit, for your time here, and let's say thank you very much for coming. I don't know if you will be available after lunch, if anyone is interested in discussing with you.
Yeah, sure. I'm leaving actually tomorrow, so
okay.
I'm available.
So if there's anyone interested, you may perhaps just tell him just right now so that you can organize also your afternoons. Okay, so thank you very much again, Pau.
Yeah, so we didn't get to talk very much yesterday. So if you try, we can still.
Yeah, sure. I'm happy to discuss with you. Yeah. Sorry, I think I was a bit too slow at the beginning, and then yeah, you know, like when you have 10 minutes talk, you can really practice it.
Exactly.
But this time I didn't have time to kind of time it. So
I think you gave a very nice overview of your, let's say, your full career.
Yeah, no, it was also actually, I actually enjoyed a lot preparing this presentation, you know, because it kind of combines like, you don't get that many chances to kind of tell your stories. So yeah, that was really nice.
I enjoyed very much. Yes, as question, because that was also, let's say, a way also to mention at least a little bit the project. Yeah. Actually, let's say at the very beginning, I didn't know whether to mention your application to Francesca's lab or not, because, you know, I didn't know how, let's say, quiet you would like to have this application. So then I said, okay, so I didn't ask you. And just in case I didn't mention anything, you know.
I mean, my boss knows, like,
he knows.
I mean, to me, that's the nice thing about science, right? You don't need to keep things secret.
But I think it also depends on the bosses, right? I mean,
exactly.
There are bosses where you wouldn't want.
Exactly. So there are other bosses that may think, oh yeah, but he's already leaving, you know. So, yeah. So then, just in case, as I didn't ask you, and sorry for that. So
I Gerhard fully supported this, so I'm super happy.
Then it's fine. Then I should have mentioned at the beginning, but I didn't know, so I decided just to be the careful side, you know.
Okay, then you just, I mean,
we
drop
go
me a note
for
or so. When you,
and then I bring him to your office or whatever.
Yes, or I mean, to mine or to his.
Or to his office, so that I let you know.
I mean, I don't actually. I have a meeting at 3. So maybe
Okay,
then
so then
it's
perhaps when you finish, you
because
we
then
can
you
go to
probably
his office.
I
We
think
will be
that
back.
it makes more sense. Thank you very much.
Yeah,
sure.
we will arrange some paperwork, but then we will go for answer. I think at 3, the latest, we will be here. So then if I leave him in his office, then okay.
Okay, where do I go now?
Let's go upstairs to make some of the paperwork, just to make, let's say.
Okay,
Okay,
then
yes,
have a weekend.
I don't know, do you think it was like?
I mean, it was, yeah. I mean,
Because
to me, it
some
was
people
because
don't
I'm
like
not, I'm not an expert, in the field, and I was lost in some of the parts, but I think that's what. But I think I could follow. Okay, I think it was.
Because usually we give talks like in quantum optics community.
Sure, exactly. So it's difficult, let's say, so, no, but I think it was very well prepared. I mean, the only pity was use the time, but how to measure time, this is complicated. So at the end, let's say with time, at least this is what I do. I try to make an average of the time that I spend with one slide. Right? That there are people that they spend 1 minute per slide. Some other people they spend 2.5 minutes per slide. So depending on your own average per slide, then you can somehow estimate the number of slides that you need for the time. For long talks. I mean, when this is short, it's not the same because then.
I think the point is that I was expecting like a more senior audience,
Okay.
Like more, but I saw many students, right?
Well, half of them.
Okay, sorry, because I was expecting like expert scientists, and then when I saw that they were like students, and I tried to explain things.
No, I think it's very much appreciated, not only by students but also by seniors, because they're quite often. I don't know if I mentioned that, porque estamos hablando de nueva cuenta. Sí, yo creo que siempre, o al menos yo, ¿sabes? Que tenemos tendencia a explicar las cosas en un nivel que nos parece que no es muy complicado, pero lo es. Pues, claro, tú eres el mayor experto en lo que estás haciendo. ¿Sabes? Entonces, claro, lo que a ti te parecen cosas triviales, hay mucha gente que le pueden parecer cosas muy complicadas. Entonces, siempre tenemos el miedo ese, eso yo a mí no lo tengo, pues, explicarlo bien, con las cosas muy profundas, es que muchas veces no hace falta papel. Pero sí, no, está muy bien, está muy bien, Pablo. Yo creo que sí, solo olvida apenas el tiempo, pero sí, no. Es que no sé si hay que firmar algún papel y sobre todo, ¿tienes gastos más allá? El avión, ¿te lo habíamos reservado desde aquí o lo has pagado tú primero?
El hacia aquí.
O sea, el viaje.
El viaje. Sí, creo que lo pagué yo. Sí.
Entonces hay que. Pero eso, simplemente, o sea, no hay que hacer ahora los papeles, pero para que ponerte en contacto con la administración para que luego les mandes todo, ¿vale? Si te dejas algo. ¿Tenías el pasador, era tuyo o era de aquí?
No, era de
vale, y cable del cargador y así del portátil tienes. Sí. Vamos a tomar una receta.